Today we will be doing haloalkanes and haloarenes. First of all, we will discuss the preparation of haloalkanes and haloarenes. The most common method of preparation is from alcohols. So in case of alcohol, what happens is that the hydroxyl group of alcohol is replaced by a halogen. For example, if you look at this reaction, alcohol plus HCl in presence of zinc chloride. Zinc chloride is playing the role of a catalyst. The OH group is getting substituted by chlorine. So this is how we can get it from alcohols. Now the thing is that in this particular reaction, the order of reactivity is found to be 3 degree greater than 2 degree greater than 1 degree. In fact, in this particular reaction, if you take 1 degree or 2 degree alcohol, then you need to take concentrated HCl and ZnCl2. But if you take 3 degree alcohol, then simply concentrated HCl is enough. ZnCl2 is not required. So this is the first method of preparation from alcohols. Incidentally, this order of reactivity is applicable for other reactions also. For example, the second method is you can see that the OH group is getting substituted by halogen. Then another method is you take phosphorus trihalide. The halide has to be chloride or bromide. Phosphorus pentachloride. So with phosphorus pentachloride also we can get haloalkane. So alcohol with red phosphorus halogen is giving haloalkane. Then alcohol plus SOCl2 gives haloalkane plus SO2 plus HCl. Now among these methods, the last one is considered a very good method of preparation because at the end of the reaction, SO2 and HCl escape as gas. So this one is a preferred method among the other methods. Now, all these reactions involve replacement of OH group with halogen. These reactions are not possible for haloarenes. The reason is that due to resonance in haloarenes, the carbon OH bond has a partial double bond character. It's difficult to break. So these reactions are only for haloalkane preparation and they cannot be used for haloarenes. The second method is halogenation, free radical halogenation. Free radical halogenation has got a drawback that you will get isomeric mono and polyhaloalkanes, and they are all difficult to separate. So you can see that this is butane, and after halogenation you are getting two isomeric monohaloalkanes. You may also get polyhaloalkanes, and it's very difficult to separate them. So this method is there, but we do not use it. Now we come to a very useful method of preparation of haloarenes. Suppose if you react benzene derivative, suppose toluene with halogen in presence of iron. Iron is playing the role of a Lewis acid. So you know that whenever there is a Lewis acid involved, you know that definitely it is a electrophilic substitution mechanism. So a hydrogen in the ring is substituted by a halogen, and that can be done in ortho position or para position. So as you know that toluene, the CH3 group is weakly ortho-para directing, so the halogen will enter either at ortho position or at para position. Now this particular reaction is very suitable for it. It is very suitable for chlorine and bromine. Now the problem is that for this is suitable if you use the halogen as chlorine or bromine, but if it is iodine, then in the reaction mixture you must have a strong oxidizing agent such as HNO3 or HiO4, right? And this reaction is not suitable for use with fluorine because of the very high reactivity. So we do not use this reaction to get fluoroarenes. The next reaction is Sandmeyer reaction. In Sandmeyer reaction, what we do is that we treat aromatic amine with NaNO2 plus halogen acid. So as a result, you get diazonium halide. Now diazonium halide reacts with either Cu2Cl2 or Cu2Br2 to give the haloarene. In case of getting iodoarene, you don't have to use Cu2Cl2 or Cu2Br2, you use potassium iodide and that will give you the iodoarene. So for chloro and bromoarenes, this is the reaction, and for iodoarenes, this is the reaction. Now in case of Markovnikov's rule, suppose this is an alkene, so you know that there are two products possible when reacting with a halogen acid. So out of these, the major product is this one. So this is a reaction which is very well known, it was done previously. So this is the fifth method, that is using Markovnikov's rule. The sixth method is, if you react an alkene with bromine CCl4, then the reddish brown color of bromine will get discharged and you will get a colorless product. So in fact this one is called a vicinal dihalide. Vicinal because the halogen is added to adjacent carbons. So this is that very famous reaction test for unsaturation. So reddish brown color of bromine is discharged to give colorless vicinal dihalide. Now the thing is that most of the reactions which have been discussed, they are pertaining to either chloro or bromo alkanes. So now we will discuss iodo and fluoroalkanes. Now there is a reaction known as Finkelstein reaction. In this reaction, what happens is that the halogen, which may be chlorine or bromine, is substituted. The halogen may be chlorine or bromine, and it is substituted by reaction with NaI in presence of dry acetone. So you could call this a halogen exchange reaction, because one halogen is exchanged by another, that is iodine. So this is Finkelstein reaction. Similarly, in case of fluoroalkanes, this is the reaction. Here AgF can be used, or we can also use Hg2F2, COF2 or SbF3. So AgF can be used, or we can use Hg2F2 or COF2 or SbF3. This reaction is known as Schwarz reaction. So this is to prepare fluoroalkanes, and it is another example of halogen exchange. Now we come to chemical properties. In chemical properties, first of all, haloalkane, when reacted with magnesium in presence of dry ether, gives Grignard's reagent. And Grignard's reagent has many uses. For example, when you hydrolyze Grignard's reagent, Grignard's reagent, you get alkane. Then next is Wurtz reaction. So in Wurtz reaction, we take a haloalkane and react it with sodium in presence of ether to get an alkane. So these are examples of chemical properties of haloalkanes. Now, nucleophilic substitution in haloarenes. Suppose there is a chloroarene. So when you react it with aqueous NaOH at a certain temperature and pressure, in presence of dilute acid, so when you perform the reaction, NaOH at 623 Kelvin, 300 atmosphere, in presence of dilute acid, you can convert it to phenol. Now the same reaction if there is an electron withdrawing NO2 group, then we get a haloarene. Then we get phenol derivative with NO2 group. Now suppose if there are two NO2 groups, if there are two NO2 groups, then the condition is NaOH 368 Kelvin and H+. So you can see that as you are increasing the number of NO2 groups, the conditions are also changing from 623 to 443 to 368, and if there are three NO2 groups, then you just need warm water So this is example of nucleophilic substitution reaction in haloarenes. So you can see that nucleophilic substitution is not very easy to achieve, and if you increase the number of electron withdrawing groups, then the electron density on the ring becomes less, and then nucleophilic substitution becomes more easy. Now one thing which is very clear, that the NO2 group has to be present at ortho or para position only. Now let us see why this is so. Suppose if the NO2 group is present at meta position, if the NO2 group is present at meta position, then this is how the reaction will proceed. The nucleophile will attack and there will be delocalization of the ring electrons as shown over here. So this will be the second resonance structure. This is the third resonance structure. Now you will notice one thing, that in all the three resonance structure, the delocalization is happening only at ortho and para positions, and the carbon containing the NO2 group is not participating in the delocalization at all. So that is the reason why the NO2 group has to be present only at ortho and para positions. So the NO2 group has to be present at ortho and para positions. That is the, and you can see that after this is the final product. But this is not a feasible reaction because the NO2 group, the carbon containing NO2 group is not participating. That is why nucleophilic substitution is not favored when the NO2 group is at meta position. Now speaking of nucleophilic substitution of haloarenes, we saw that it is not an easy reaction to perform. Now what could be the reason for this? Why is it not an easy reaction to perform? First of all haloarenes have resonance. You can see that all haloarenes are resonance stabilized. So due to resonance, the bond between carbon and halogen has a partial double bond character. So it is not easy to break this bond. The second one, is that suppose this is a haloarene, you can see that this carbon is sp2 hybridized, whereas this carbon is sp3 hybridized. This is a haloalkane. So you know that sp2 is more electronegative, so that is why it can hold the electron pair of carbon halogen bond more tightly. So this bond is shorter and stronger, whereas this bond is longer and weaker. So that is another reason. Number 2, and number 3, what happens is that the phenyl cation is not stabilized by resonance. So because the phenyl cation is not stabilized by resonance, that is why SN1 is not possible. That is number 4. And fourth very obvious reason is high electron density. So it's quite clear that there will be high electron density on the ring. That is the fourth reason. Now, we know that the halogen group is ortho-para-directing. Now the problem is, although the halogen group is ortho-para-directing, but due to minus I effect, it also has a tendency to withdraw electrons. So as a result of that, electrophilic substitution reactions of haloarenes take place only under certain conditions. So what happens is that if you want to halogenate the ring, it has to be done in presence of anhydrous FeCl3. And as expected, you will get the ortho and para product. This is halogenation of the ring. Suppose we wish to perform nitration of the ring. Suppose if we wish to perform nitration of the ring, then it can be done like this. HNO3 and concentrated H2SO4. Concentrated H2SO4, this is sulfonation. Friedel-Crafts reaction. Friedel-Crafts reaction. So this is Friedel-Crafts alkylation. And this is Friedel-Crafts acylation. Right? So Friedel-Crafts alkylation and Friedel-Crafts acylation. So these are all examples of electrophilic substitution. Now we already know about the famous Wurtz reaction. Now we come to Wurtz fatigue. So in Wurtz fatigue reaction, we have haloarene, sodium and haloalkane in presence of dry ether, and then there is also the fatigue reaction. Fatigue reaction is two molecules of haloarene will combine with sodium ether as follows. So these are the chemical properties of haloalkanes and haloarenes, and with that we come to an end of this particular session of haloalkanes and haloarenes.